The entire lecture series is Physical Chemistry 4, Molecular Dynamics and Electronic Structure. And we will really focus more on the electronic structure. The electronic structure allows us, and we will discuss this in quite some detail, to obtain forces on all atoms, okay? And these forces are one of the most crucial ingredients for doing molecular dynamics. And so in PC5, you will actually discuss in more details molecular dynamics and statistical mechanics. So that part will take place actually more in the future. We focus here in this fall semester, we will focus really on the electronic part, which forms the basis then for the dynamic part, okay? Roughly speaking, we have 11 chapters, and depending on the year and depending how things progress and depending on the discussions we have, and I haven't said it yet, but I'd like to stress it, I really welcome discussions. So if you have any questions or comments, please feel free to interrupt me, and we'll talk about it. So depending on that and depending on the speed we progress, we will or we will not cover all these chapters you see here, okay? So we start out in chapter 1 with the introduction. That's something we'll do today. We'll have then a rather lengthy chapter on the blackboard on theorems and postulates, a rather short chapter on the variation method. The perturbation method theory is also rather short. Chapter 5 on molecular quantum theorems is longer than again. In there we will discuss the covalent bond in particular, the chemical bond, right? What is a chemical bond? How can you understand it properly? Then after chapter 5, we will go back to slides and the chapters on Huckel, Hartree-Fock, DFT, or correlated methods. These are all numerical methods for which computers are being used, right? So up to 5, you can do everything with pen and paper. Huckel in parts you can still do with pen and paper, but it's more of a calculational thing. Up to 5, it's more derivations and relationships. And then for chapter 7, 8, and 9, you typically need a computer to solve the equations. And maybe in the exercises, you will also discuss one such computer program, how it might look like, but this will be up to Moss. In chapter 10 and 11, we have 2 sort of technical parts that are extremely relevant for the research field of electronic structure. But if we don't cover it in this introductory course, then it's not a big drama. It's not so bad, right? It's not so important. If you decide after this course that theory is not for you, then you don't need these. If you decide that theory is for you, then you will encounter them anyways. So in any case, they are rather there for completeness if we happen to have more time than we might need. All right, with this, I'd like to change now to the introductory, to the introduction section, unless there are any more questions. I don't see any. Again, you can also post your questions in the chat. If you don't wish to interrupt me, the chat window is open here, and Moss can also look at it and can also provide answers while I'm talking. So feel free to do as you wish. All right, so I'm changing now to the introduction chapter in our lecture series. All right. Until recently, I used to be a professor at the Department of Chemistry Last year, I accepted a new position at the University of Vienna and the Faculty of Physics. But my colleagues and I agreed that until they found somebody else to replace me, I would still do this talk, this lecture series in particular. So I still have my Unibus email address if you wish to write to me, and that should be valid until next spring. In terms of literature, this is a classic topic in the chemistry curriculum, so you will find plenty of texts on this, right? And this is really just a selection here. You might have encountered the Atkins in physical chemistry. The Atkins is a very popular book. I'm not particularly fond of it, but there's also one for quantum chemistry or electronic structure. I don't recall exactly how it's called. If you like that very much, then go ahead and use it. The books I would recommend are indicated here. The easiest and most introductory one is the book by Macquarie on quantum chemistry. There's also one by Levine called Quantum Chemistry, which is a little bit more advanced. But these two books, they really explain everything in very great detail, right? So you should be really able with what is described there to follow up on each and every step that's happening. So these two books are meant as really the most basic books, and much of this lecture is also in one way or another condensed or distilled from these two books. Then there is the third book. The third book is rather an advanced book, so I would not recommend going after the third book, the Sabo and Ostlund. I would not recommend reading this before you have not read either one of the first two. And the fourth book is sort of in between the first two and the third one. Okay, I mention it here because I consider it really to be a great classic. Linus Pauling is, of course, the chemist who described the chemical bond. And E. Bright Wilson, actually, he did not win a Nobel Prize, but he was a fantastic physical chemist who wrote multiple books which are really classics in the field. And so this also comes through in this piece. And so I'm very fond of this book. And there's a lot of superior insights in there. So even when you are very deep insights, so even when reading it multiple times, you will find new ways of seeing things, and so it's just a wonderful book. I should also remark that since this is physical chemistry, units are extremely important, and you should have learned already in high school that units are not only important so that you can compare apples to apples, but they also indicate fundamental relationships and what's also known as dimensional analysis. Okay, so for instance, they tell you if the length is quadratic or cubic or directly linear, and that means a lot, right? So, and if it's in the numerator or in the denominator, so these are all important aspects, and so one should consider this. But in this lecture series, we will basically make our life easy by using atomic units throughout. And this is something you should have learned to know already in your introductory PhysChem lectures. And so I'm not going to explain them more, but you should realize that this is very much exploited here. And whenever you feel bored, if you ask yourself, okay, what would be the SI units now for this quantity, that's always a useful exercise. So I'd strongly encourage that. I should also point out that the mathematics we use is maybe among the most advanced you will need in your chemistry curriculum, but it's also not super advanced in absolute terms. So if you study physics or if you study mathematics, obviously you would have to go way beyond what we have here. And basically, we do not go much beyond of what is part of, I would argue, high school mathematics, right? If you have a high school exam in mathematics, you should be fine. The introductory math courses offered at the University of Basel for chemists should also suffice. We have checked on the content there, and you're always welcome, of course, to go back to those if ever you find that at loss with something and you don't want to discuss it openly with your assistant or with your colleagues, then you're always welcome to go back to those courses. Actually at University of Basel, I think they do really a great job for beginning students in terms of mathematics as well. All right, so with this, let's see. So these slides are, the text is still in German. I'll talk in English, I hope you don't mind. And I'd like to sort of launch the lecture by asking a rather simple question, which is, what is a molecule, right? So I'd actually like to ask you this question, and now you could type your answer in the chat or activate your microphone. Would be nice to see some opinions here. So how would you define a molecule? Okay, here's a nice suggestion in the chat, basically a collection of atoms. I think that's already a good start. So the atoms and the molecule. Another one, another definition coming in, a structure consisting of multiple atoms connected via bonds. Very nice. At least two nuclei glued together with electrons, also very nice. I like it. So the answer to this easy question is not as easy as that question, right? You can see already the answers offered by your colleagues, they vary a little bit. It's not always the same, right? This is, of course, something quite common in science, that simple questions have tricky answers, right? So by the simplicity of the question, you may not infer about the simplicity of the right answer, at least. So if you Google this question, or if you Google a molecule, right, you see here a definition. I copy pasted, where it basically says so it replaces molecule by chemical compound, right, which has some properties of that compound, right? So, but made up of atoms. So atoms are mentioned, and also bonds are mentioned, and that these bonds have something to do with electrons, right? So it goes a bit in the direction of what some of you have offered in the chat, right? It's a bit unsatisfying though, right? I think you can see that we could, so the bonds that form have not yet been defined, right? So you define A by introducing B, but B wasn't defined. So we're playing a little bit of a game here, right? There's this definition glued together with electrons, right? That's a very appealing definition. Among the three offered, I like it the most because it actually implies that you have some something that has an optimum distance, right? When you glue, it means they're stuck together, and that electrons matter for that. So the bonds, you could also argue, well, that's the meaning of a bond, but that we haven't defined that yet. Bonds are not elementary particles, right? So part of my job in this course is also to make you question a little bit the chemist's notion of the chemical bond. Right? So we want to revisit this notion, and we want to rethink it a little bit. As I said, bonds are not elementary particles. Right? In fact, bonds are not even observables. Okay, so it's a rather tricky thing, actually. And despite the fact that so many use this term bond, despite this fact, it's actually questionable how to define it. Right? It's open for debate. Now, as a natural scientist, we don't like that, right? We'd like to have the one answer, right? The one true law. Right? And so we try to put this on a little bit more rigorous grounds, in particular in this chapter on the molecular theorems. We will revisit this question of the bond, right? Okay. Now, here you see three illustrations of molecules, and none of them is wrong, right? But you clearly see a very strong difference among them, right? Now, let's start on the right. On the right, we have a mathematical graph where you have the edges, right? So these lines which are meant to symbolize bonds, and you have the vertices which are meant to symbolize atoms. And so some atoms have been specified, some not, right? So there's a lot of implied knowledge here. So you also have, in particular, you have some aspects of this graph that allude to a three-dimensional structure, right? Now, if you look at the center molecule, right, you actually see the 3D structure, right? And it becomes much more obvious, right? Your atoms live in a 3D space, and this is clear from the mid illustration. If you go to the right-hand side, it's just a projection on a 2D surface, and but there are no electrons. So only if you go to the left, you actually get an idea of the electrons, right? And so what we actually observe are these electrons, right? It's not, we don't see those bonds, these sticks, these vertices we like to draw, you cannot see them, right? What you see are these electrons. And here's an actual experimental figure, not something drawn up by a theoretician or simulated by a computer program. This is an atomic force microscopy picture recorded with a machine, right? An experimental observation of this molecule here on the right, adsorbed on some surface, right? And that's how it looks like, right? And what you can see here are the electrons, right? And you can see some structure here, right? But really, it's very light where the nitrogen is, for instance, because nitrogen has more electrons than carbon, right? Now, you also see something counterintuitive. Your oxygen should also have more electrons than your nitrogen. or your carbon, but you actually hardly see it here, right? So this could be because these atoms are not that close to the surface, and so they actually less, you see them less, right? And so what I want to evoke with you or create with you is this realization that the idea of what constitutes a chemical, right? And what constitutes a molecule or any compound, this is something we have to consider, right? If we want to have a rigorous understanding of chemistry, that is, right? And so this idea should account for what we measure. It should be consistent with all the laws of physics. It should be consistent with everything we know, but it should not go beyond. It should not presume things where we don't know, right? And so this is a little bit the goal of this lecture series, to also try to start that kind of thinking with you. Now, why is the electronic structure so important to chemistry? Well, there are various definitions of chemistry, and some cynical physicists just call it the physics. Chemistry is the physics of the valence electrons. So this is partly true, right? But if you have nuclear quantum effects, so for instance, your hydrogen atoms, they have such a small nucleus that also your nucleus can have a quantum effect, right? That can also affect your chemistry. So you hopefully have all heard of isotope effects, right? For instance, the kinetic isotope effect on chemical reaction rates. That's an effect that comes due to the nuclear nature and the quantum nature of the protons. And if you substitute your protons by deuterium, you can measure this effect, right? And that has nothing to do with your valence electrons, right? So this statement, this sort of provocative statement, and number one is, as such, it's to be taken with a grain of salt, right? It's maybe mostly the physics of the valence electrons, but not all of chemistry is the physics of the valence electrons. Similarly, for relativistic effects, right? For heavy elements, these effects can be really on percentage scales of covalent bonding energies. And then if you compete among different bonds, right, this can really shift your scale in one way or the other. So I would be cautious with such global statements, right? But roughly speaking, in many cases, it's really the valence electrons that dictate the fate of chemistry, right? So that justifies the focus of this lecture, right? The electronic structure is really something very much at the heart of chemistry, and pursuing the studies of chemistry, we should all really care deeply about it. If we end up in theory or experiments later on, it doesn't matter. We should be strongly aware of this fact that it's really the electrons that matter. And I presume that most of you, I don't have to convince you, so I'm a little bit preaching to the choir here, but yeah, this is to formally state this once more so that we are all on the same page here. Now, there are, you know that the electrons are quantum particles, and then there are quantum properties, right? So if you observe the color of some compound, when light interacts with compounds, right? That's a quantum effect, right? Light is you have photons, which we like to describe as waves, and this is all what we learn in high school about the character of wave and particles. We discuss this for light first. Then we have chemical reactions when we have electromagnetic properties, right? For instance, if you go to your doctor and you get an MRI, that's a magnetic interaction with molecules in your body. This is an electromagnetic interaction, really. And so all of that is influenced by the quantum mechanics of your electrons, right? You cannot possibly explain all these effects without the quantum nature of electrons. At least you could try, but I wish you good luck. So currently the best theory that fits all of that is quantum mechanics. Now, the idea of treating electrons explicitly is very appealing because they are an elementary particle. And so in principle, whatever they do, right, if you have a working theory for that, you should be able to predict any property really that is dominated by these electrons, right? So again, the nuclear quantum effects, your kinetic isotope effect, you're not gonna be able to study it in this lecture, nor the relativistic effects, but the most common scenarios of chemical bonding are as governed by the electrons, we be able to cover, and this means that any such property, could be predicted, right? And that is, of course, what's really appealing then to chemistry, right? If you can predict the chemical processes, you can predict what will happen if you mix A and B after that amount of time, right? Will you get energy, or how much energy would you need to make a certain process happen? And that sort of control is, of course, of very fundamental importance to the well-being of humanity at large. And so this is something which is still a forefront, if you wish, of our scientific efforts. So we are trying to do this in chemistry, to predict properties of compounds, and to some extent, this is possible, right? It's not yet possible for all systems and for all properties and for all cases, but for quite many, we are quite successful. And so it's part of this lecture to get you a little bit up to speed as to how that works and how far we can get there. Now, I've noticed we passed 11 o'clock. I'd like to take a little short break, yeah, and so let's maybe reconvene at 11:15 for the second hour of this lecture. Yeah, if you have any questions now or later, you're always welcome to put them in the chat. Okay, let's continue. These points 1, 2, 3, they sort of discuss why we need electrons and their quantum mechanics. So let me circle back to the question, what's a molecule? You know from your thermodynamics that really for a molecule to be stable, if we assume stability, right? We assume that your molecule for a certain period of time is there independent of you doing anything to it. So its lifetime being non-zero, then you're implying a couple of things, right? For one, you're implying that there's energetically, in terms of free energy, there's no alternative, right? So it must be in a free energy minimum, right? And so you know that this minimum depends, the free energy minimum depends on the conditions. Right? So if you heat up things far enough, or if you lower the pressure deep enough, right? If you increase it, or if you cool it, if you throw in other reactants and so on, your molecule might not be stable at all. It might be in an instantaneous snapshot, and it might react to something else, right? And so typically what we are referring to, what we are implying by molecule, is something that will not spontaneously decompose or react, right? And that you can only have if you're in a free energy minimum with barriers around this minimum high enough to prevent your system from overcoming these barriers with any lifetime, right, that you pre-prescribe, right? So the appropriate answer to the question, what is a molecule, is really, it depends, right, on the conditions and on the height of your free energy barrier surrounding that geometry. Now note that I did not need to make reference to a concept such as bonds, right? All I had to do is refer to the free energy. Now, you know, the free energy has multiple ingredients, most notably the enthalpy and the entropy. Now, both of them account or include explicitly the potential energy of your system. And it is that potential energy that we can calculate by accounting properly for the electrons. Okay. Again, no reference to bonds, only to electrons. So as you will see in this lecture series, we will not be really making use of bonds. Most lecture series in chemistry studies make use of bonds. Right? Yeah. We will try to avoid them. We will discuss them, right? What is their meaning in the context from an electronic perspective, right? How could you account for them? But we will not use them, right? To us, it's an outcome. It's not an input. All right. So if that's our definition, right? Then the question is, how can we predict this, right? And I told you that right now the field is quite, we're quite successful already. And one of the reasons is shown on this graphic here, which, the next slide, which shows you the performance of some of the most powerful computers on this planet as a function of number of years, function of time, right? And so you see here that the performance of the computer in flops. So these are floating point operations per second. And we are going from mega to giga to tera to peta to exaflops, okay? And you see that the scale here is logarithmic. So it's an exponential thing. You every inch, it's a factor of 10, right? While time is linear, right? So the x-axis grows linearly. Your y-axis grows on this logarithmic scale linear, which means the y-axis is really growing exponentially, right? So the compute power is growing exponentially over time. Al Bartlett, whose quote I pasted here below the graphic, he was a physics professor at University of Colorado Boulder. He stated this: it's one of the greatest shortcomings of the human race is to understand the exponential function, right? You can see this in this current pandemic, right? When there are waves coming in infection numbers, people respond sort of the response is either way too late or way too early. It's hard for humans to respond to exponentially governed processes. Now, it's quite impressive, though, that the compute power has grown like this. And if you assume that the money budget for computer time has remained more or less constant, right? So, which is maybe a bad assumption, right? That prosperity has been constant over 20 years or so. But if you assume that, it means that for the same amount of Swiss francs, you can get exponentially more CPU time over time. And that is an amazing statement, right? Actually, you could assume that the value of the Swiss franc goes down over time due to inflation, like most currencies. Then the number of flops you are getting is even more impressive, right? So this is a tricky thing to normalize it. But what is most important here is that in orange you see the fastest computer. So these computers come from the top 500 list. You can go on this homepage and look every half a year. It's being updated. The fastest computer is shown in orange, and sometimes you see a sort of a plateau. This is when it's always the same computer, right? And then once there's a new one, a faster one, then it jumps. In blue, you see among the 500, the least performing one. And then in green, you see the total, so the sum of these 500, right? That one grows continuously. Now, why does that matter to chemistry? Well, it's these computers we use to make predictions, right? And so if in the year 2000 you could make a prediction, and if we assume that the accuracy or robustness or reliability of your prediction had a certain degree, right? Then you know 10 years later, or even 5 years later, you're roughly 10 times better in your prediction, roughly speaking, every 5 years. So that's amazing, right? I'll challenge you to find any other experimental chemistry and any other experimental technique in chemistry that would become 10 times better as you wait 5 years. Very few. And maybe the decoding of the genes is something that has enjoyed equal advances, right, or similar advances, right? But usually your NMR measurement will not improve 10 times if you wait 5 years. Okay. Nevertheless, right now, it's not in general possible to predict chemical behavior in a quantitative fashion, right? So if you come along with a new solvent, a new reaction condition, a new catalyst, and you ask what's going to be the rate constant for, I don't know, my aromatic substitution, that's going to be a tough one, right? And it would probably, if you're a capable synthetic chemist, it wouldn't take you long to make those measurements in the lab. So while theory still struggles with this, right? And so in some sense, this compute power is very nice, right? That is like building all the tools we need, but we still we cannot as a community and in terms of theory, we still fail in general. Right? So for particular questions, we can deliver very good answers. Right? One such question would be, for instance, reactions in outer space, right? So what the astrochemical questions, these are few atoms in vacuum that do things to each other. Oftentimes theory can work quite well for that. Or when it comes to inorganic crystals, right? So is one crystal structure more stable than the other? Actually, there we can in many cases already predict the right answer before having to measure it. But this is really a forefront, right? And so the challenge is to make this more generally work. You can even go towards a more philosophical point of view and say, well, we haven't really understood chemistry. You might be able to measure something, but have you really understood it, right? You could argue that we only understand things when we are able to predict them in a quantitative fashion, right? And that is really a challenge, right? Then it asks you, okay, down to which precision, right? Have you understood it if you can predict the thermochemistry of your reaction, or only once you also predicted all the infrared spectra of all your products of some new candidate reaction? So that kind of definition of understanding is quite interesting, because it actually conditions your understanding on what you want to do with it. If you don't care about the infrared spectrum and only about the amount of heat you can extract from a reaction, then you don't need the understanding down to the spectroscopic precision, right? But obviously, if in the infrared spectrum there's the fingerprint which helps you to detect something, then you need that kind of precision, and then you haven't understood it sufficiently well if all you can do is predict the thermochemistry. So this definition of understanding is quite an interesting. I think it's very useful. It's part of being in a rigorous science, right? If you cannot calculate anything, then you haven't understood anything at all. If you can calculate something to a degree that it is useful for you, then you have understood it sufficiently well, but you haven't understood it fully yet, right? So as a proper physical chemist, it's very hard to find somebody who would actually claim that he has fully understood any of our problems, right? Typically, we claim full understanding only for toy problems, like the harmonic oscillator, or the spherical cow, right? But not for realistic systems. There's so many phenomena acting on the outcome that it's very, very difficult and challenging to claim that you fully understood something. So I'd like to caution you against those who make such claims also, right? So your degree of understanding really depends on the precision to which you want to which something is useful to you, right? All right, so what you really have then is that you have your electrons, and they are represented by a wave function, right? So it's this wave function that we are talking about. That is the electronic structure, right? And you've encountered already Schrödinger's equation, so I don't need to tell you that there is something like a wave function, right? You know that. But if we consider a molecule now, and in particular the potential energy of this molecule that you would calculate for a given electronic configuration, then you have this wave function capital phi here on the left. And it depends, of course, on the geometry of your system, so where the atoms sit, right? And this is shown by this capital R, right? The bold capital R. Can you see the highlighted R now? You can, okay. So those are the positions of your atoms in 3D, right? And I like to give atoms the capital index I. So you have first, the second, and so on atom. Now each of these atoms has a position, but also a nuclear charge, right? That's the chemical composition, and we typically call that Z, right? Z is not bald because Z is just one scalar number, right? It's not three-dimensional. Your coordinate of your atom is and 3D, X, Y, Z, and so it's a bold number. It represents a vector. Your Z is just the nuclear charge, right? Which you can, which is the atomic number, and you know it from the periodic table, where all elements are arranged in the order of the nuclear charge. And then we have this bunch, right? The set of small r, and these small r are supposed to represent our electrons. And for now, just presume the particle view. So on any given 3D coordinate, right, in space, right, there might not be an atom, right? There could be an electron, and that is our electron I, right? And in total, you have a bunch of electrons, n electrons. The number of electrons for a neutral molecule would be equals the sum of all the nuclear charges. So these things you know, right? You're already sufficiently advanced in chemistry to know that. And the wave function of the entire thing, right, of the entire molecule, must depend on all these quantities. These are the elementary particle quantities. Now, you could argue, of course, what about the neutrons? Right? So the Z, the nuclear charge, is the number of protons in your atom I, right? You could argue, what about the neutrons? Right? They are also there. It's true, but they don't affect your electronic Schrödinger equation. Right? They don't affect your valence electron. Right? They will affect your dynamics, right? And they will have nuclear quantum effects for light atoms. Right? But for this electronic wave function, we don't really need it. And what we typically do is something called the Born-Oppenheimer approximation. And I apologize for this. This equal sign should really be an approximate sign. So we approximate this full wave function, right, of nuclei, their nuclear charges, and the electronic positions. We approximate this one as a product of two wave functions. And that's an approximation, right? This approximation is known to also break down in some cases, but it's a fairly good approximation in most cases, in particular when it comes to bonding, right? So when we are in this minimum region where atoms bond, right? I'm not talking about bonds, just that the fact that as atoms come together, the energy lowers. And in this region, this approximation is typically a pretty good one, especially for the electronic ground state. Now, in this electronic ground state, we then write this full wave function simply as a product of an electronic wave function, which only depends on the electronic degrees of freedom, and a nuclear wave function, which only depends on the coordinates. So the Born-Oppenheimer approximation is really a product ansatz, where you separate the degrees of freedom of the underlying elementary particles, okay? So you can basically fix your nuclear charges and your coordinates, and then ask the question for that fixed geometry and that fixed composition, how do the electrons arrange, right? And that is what the Born-Oppenheimer approximation accomplishes. Now, it makes the problem much more intuitive, okay? In particular, it results in the so-called time-independent many-electron Schrödinger equation, okay? This Schrödinger equation takes this electronic part only, and it applies some Hamiltonian to it, and out comes the electronic energy as an eigenvalue for that geometry, right? So that's really appealing. So then you can ask this question, okay, as I change my geometry, how does this eigenvalue change, right? And then if you stretch the distance between atoms, right, then you should see in the limit that your atoms are far away, they don't interact anymore, right? So your energy will not change anymore. It's just the sum of the two free atoms. And as the atoms come together, they should first feel some attraction. So the energy should go down. And then at some point, they should feel some repulsion. So the energy should go up again. Right? So based on these very simple arguments, right, you can already infer how this electronic E, this EE here in equation 2, how it looks like as a function of distance between atoms. Okay. Now, you've already encountered Hamiltonian operators, right? You know how they are typically being constructed by correspondence principle, right? This is also what we do for the electronic structure, right? So we say our electronic Hamiltonian, and that's basically being postulated, right? Contains three terms: a kinetic term, and this kinetic term has the typical quantum mechanical expression. It's the curvature operator, right? So second order derivative in space. It's the external potential. We come to that in a minute. And it's the interaction between electrons. And simply, we assume that the electrons in this operator, they interact as through Coulomb interaction. So 1 over the distance, right? So electrons repel each other, right? So that's what you see here. There's a positive term, it's a repulsive term. If the electrons can move around a lot, right? If they have a lot of kinetic energy, then you should gain energy, right? So it's a negative part. Here in front of the kinetic part, and in the external potential, what is this? This is the term that lets your electrons interact with the nuclear charges, right? So this is the term where you sum over your nuclei, capital I, right? And you have to do this for every electron. So you also sum over the small I, and every electron is at a distance from some nucleus capital I, and the interaction, of course, the bigger the nuclear charge, the more the electron gets attracted to it, right? So that's what you have in the numerator. Now, electrons are negatively charged, protons are positively charged. So when they interact, you should gain energy, right? It's not repulsive, it's attractive. So you have a minus sign in front of it. Now, these are the three terms in your electronic Hamiltonian. The total Hamiltonian also contains a term where the nuclear charges repel each other if you have multiple atoms, right? So that's just the nuclear charge of atom I with the nuclear charge of atom J divided by their distance, right? So that term is not shown here because it's not part of the electronic Hamiltonian. It's the total Hamiltonian, right? So that's what you see here now, right? That's the total energy, is the electronic energy you get by applying this electronic Hamiltonian to your electronic wave function, right? It's this electronic energy, and then you add the nuclear repulsion term. Okay. So it's quite funny, even sort of grown-up advanced experts in the field are not aware of the fact that if you actually ignore the nuclear repulsion and you only consider the electronic energy, you would never have the repulsive part in the binding potential. As your atoms come together, your electronic energy just keeps on coming down. And eventually, once your atoms are fused, you have what's called the united atom energy, right? So that will be the atom without any other nuclei, right? So without nuclear repulsion. So suppose you have two hydrogen atoms and you fuse them together in the H2 molecule, they become helium, right? And helium has no nuclear repulsion, there's no other atom, right? So it's really this classical nuclear repulsion term here in equation 6, which takes care of the fact that the two atoms should repel each other. They repel each other because of the nuclear charges. Two protons at different places in space, they will repel each other. Same charge, right? Simple classical electrostatics. That's what's causing the repulsion.
Sorry, can I
Yes,
can I
please.
ask something?
Of course.
I wondering in the where you divide the external potential, you have first two sums over I and capital I, and then after the second equal sign, you only have one sum over capital I. Shouldn't there also be the sum over small I?
Yes, you're right. No, you're absolutely right. This should actually be, yes, we are missing the second sum. That's correct.
Okay, thank you.
Thank you.
Sorry, can you repeat that mistake?
So the V in the middle of equation 5, right, was replaced by this fraction of z over the distance, but you still need the second summation symbol.
Oh, okay. Yeah, thanks.
All right, good catch. Thank you very much. All right. So the picture that emerges then is something like shown here, that when you plot this total energy on the axis here, the vertical axis, right, as a function of 2 degrees of freedom, let's say 2 positions, okay? You can plot this energy, right? Let me go back here. This total energy, E total, and this is called then the total potential energy hypersurface. Why hyper? Because it can have as many dimensions as you have atoms in there, right? So it's not just 2D. It's in principle, it's as many dimensions as you have in terms of atomic degrees of freedom. So typically, for any given system with a fixed composition, right, with a fixed stoichiometry, you would have 3n minus 6 degrees of freedom, just like in the vibrational spectroscopy problem, which you've already discussed in PC3, right? So as a function of these degrees of freedom, you can plot out the total potential energy. And so because there's more than 3 degrees of freedom, typically we call it the hypersurface, right? Now you can plot the surface, and then you will encounter minima, right? So these are geometries where you have binding, right? And you will encounter saddle points, transition structures, right? Of first order or second order saddle points, right? You might encounter another minimum. And you see, this is the total potential energy surface. Now, that is an integral part of the enthalpy, right? And you can also use it to calculate the entropy by Boltzmann's formula. Right? So this is what enters your free energy consideration. If you now assume that you're working at very low temperatures and that roughly this surface corresponds to the free energy surface, then you can think of this in terms of the surface on which your compound lives, so to speak. And if you started out here at some temperature, it would cross over here with a certain lifetime probability. And then this would be the global minimum, and this would define your molecule and answer the question with which we started today's lecture. So the calculation of this total energy, which you can also write as the expectation value, of the inner product of your Hamiltonian working on the wave function with the wave function is thus essential to obtain, to predict free energies, to predict rates, to predict entropies, and so on. And that's something you will encounter then in more detail in statistical mechanics, how you will use this, right? This lecture series is about how do we calculate this? How do we get this? Okay, let me go back here. You see again our Schrödinger equation, right? So we multiply from the left with psi. Okay, then your energy is just a number, so you can pull it in front of psi, and you have psi times psi, and here you have psi times h applied to psi on the left side, right? And then you integrate over the whole thing, and then psi multiplied by itself, integrated, if normalized, becomes 1, and so your total energy here, the energy, and you can always add this classical term here, this energy is then the expectation value, or this this expression here, right, in bracket notation of your Schrödinger equation. So once we come to the subsequent chapters, we will do this by hand, and we will encounter this all the time. Now, it's very important to realize that in quantum mechanics, there are more operators than just your Hamiltonian. Your Hamiltonian is so very special because it gives you the energy, and the energy dictates or governs the fate of your processes. But there are more properties, right, than just the energy. For instance, the dipole moment, right, of your system. Right? And it's the power of quantum mechanics to also tell you how they would look like. Right? Now, what you need for that is an operator, the operator of the property you'd like to have. Typically, we get this operator by the correspondence principle. So if you got your wave function by solving Schrödinger's equation with the Hamiltonian, then you can use this wave function again to calculate the observable of some other operator, and that will result in the property of interest. So it's very important that if you have not yet realized this, that this is one of the reasons, or maybe the reasons, why quantum mechanics is so immensely powerful and so incredibly elegant, right? So once you have that wave function, you can calculate any of its properties, and that's how you do it, by evaluating this expectation value. Now, this also gives rise then to the first postulate of quantum mechanics, and we will cover those as well in this lecture series. And the first postulate states that your system is the wave function, right? So we asked before, what is a molecule? A molecule is typically something to be considered stable, so something that lives in this minimum. But your system can also live for very instantaneous lifetime, right? For any other of these configurations, right? And so instantaneously, your system is then defined by that Hamiltonian and its wave function. So any grid point on your potential hyper energy surface, any grid point corresponds to a different wave function for which you have obtained a different solution to Schrödinger's equation and a different energy. And for any such grid points, you can then evaluate its dipole moment or some other property. Okay, so your system, for any geometry, for any situation, the system is really then defined by this wave function. Now, one example of such an observable would be to calculate the forces. And we do that in a minute, maybe not today, but tomorrow. But That's a very simple operator which we can use, and then we can evaluate this integral. But you could also be interested in the frequencies. So basically the second order derivatives along your binding modes, right? You could be interested in dipole moments. This is actually the dipole moment. You can write this also as an expectation value in terms of your wave function. If you realize that the wave function squared gives you the electron density, typically exemplified by the symbol ρ. You could also look at polarizabilities, right? Polarizabilities measure how your dipole moment changes if you applied a field to it, right? You know already from heuristic and empirical discussions that a floppy large system with a sloppy electron density will respond to a field more than something with a very tight small core like a fluorine atom, right? So as you go down the halogen column, and as you should know already, your polarizability goes up because your electrons populate a larger space, always around the same atom. You have one atom and your electrons grow more and more, and so it's natural to expect that the response to an electric field will be stronger. So you can more easily induce a dipole moment, and that is what polarizability quantifies. How strong is the induced dipole moment with respect to the reference or the static dipole moment? This is what polarizability means. Now, you can also use this formalism to get other properties, infrared or Raman intensities, NMR shifts, electronic, the ESR spectra, all sorts of properties, right? So this is the claim to fame of quantum mechanics, that it can account for it all. All right, so let's get started with the forces on the atoms. And you can, by classical mechanics, ask yourself, what is the force? It's the derivative of your potential energy. And so we derive this potential energy with respect to a change in the position of your particle. In this case, the particle would be not our electrons, but the position of our atom, right? So if you're moving atoms around and you're monitoring the energy as a function of distance, you get this binding curve, then the force is just the derivative of this curve, right? So that's what you see here, right? The energy, the derivative with respect to displacement in the dimension x with xyz, right? So for every dimension you can do this, of atom I, right? And since you can displace in all three directions, your scalar energy field becomes a vector field, right? For every coordinate, for every geometry you can think of, right? Let's go back to our hypersurface. Any one of these grid points has an energy value attached to it, and you can ask the question, how does this energy value change if I change my atom in X, in Y, or in Z, right? So at every grid point, you don't only have the energy, that will be a scalar field. What you're seeing here is a 2D scalar field. You also have the 3D vector field in that 2D, in the 2D dimensions you're seeing. So in the 3n-6 degrees of freedom, your forces form a 3D vector field. Now we are considering your vector element for the displacement in X, and we use something called the Hellman-Feynman theorem, right? And this tells you also something. This theorem, I give you the reference from Richard Feynman, Nobel Prize in Physics. In 1939, his master thesis was this paper on forces in molecules, where he derived how you can calculate from basic quantum mechanics the force of an atom in a molecule. Now, Hans Hellmann was a German physicist who did this already 10 years before that, but he escaped to the communist side of things, and he published in Russian obscure journals, and so his equations and derivations were sort of lost. And so Feynman really established it, but then people realized, of course, that it was not the first. And so now it's well known as the Hellmann-Feynman theorem. And there are even some debates, there are also other names attached to it, but this is how it's most commonly known. Now, the Hellmann-Feynman theorem states that this derivative of your energy with respect to any variable in your Hamiltonian, let's call it lambda, right? So this could be your nuclear charge. This could be your coordinate x, y, or z of atom I, right? You have n atoms, right? So you have all the 4n possible values, degrees of freedom here. This derivative must be the derivative of this expectation value. This we discussed already. This is nothing else than your energy. And what Hellmann and Feynman showed is the right-hand part of this equation 7, that this is nothing else than the expectation value of the derivative of the Hamiltonian. Right? So that's not obvious. It's wonderful, but it's not obvious, right? Why this should be the case, right? It's basically saying that your wave function doesn't depend on lambda, not to first order at least. That's what it's saying. So why should that be the case, right? That's not obvious, as I said. So I'd like to tell you about that tomorrow. We will revisit this theorem also later on in chapter 2, when we talk more about operators. But with this, I'd like to end for today. I hope you enjoyed this lecture. If you have any questions now, please post them in the chat. I'd like to thank you for your attention, and I'll see you tomorrow at 9:15.
I have a question I would like to ask directly like this, if that's okay.
Sure, go ahead.
And if you just could quickly go back to the Opera approximation equation.
Sure.
Yeah, just want to ask again, what's the difference between the small r and the big R?
Very good, very good. Thank you so much for asking this, okay? So the notations are so important, and it's very important. You know, the equations we put, they really mean something. And if it's a small or a capital R, it does mean something else, right? If it's a small I and a capital I, it means something else. So the small r up here we use, so we introduce it in here. We always use it for the electrons, right? You throw in an atom into your molecule, right? Suppose everything is neutral, okay? So you throw in a neutral carbon, you have 6 protons, right? Nuclear charge 6, and 6 electrons you're throwing in, okay? So these electrons sit somewhere, and that's what we use the small I for, okay? So the small I runs over your 6 electrons. Now, if you have multiple carbons, and then if you have n carbons, then you have n times 6 electrons over which the small I has to run.
Okay, thank you. So the molecule's wave function depends on the wave function of the electrons as a product with the wave function of the nucleus.
That's the Born-Oppenheimer approximation, that you may do this, right? Strictly speaking, and in general, it's not true that you may do this, right? Okay. It means basically that if you vary an electron, right, your nuclei would not care.
Yeah.
But that's not true in general.
That's
right?
true. Okay.
So it's an approximation, but it's a pretty decent one. And typically, it's the heavier the atoms in comparison to the nuclei, the better it is, right? So if your electrons vary a little bit, right, and your electron is very heavy, then the momentum you need to get it away, to move, to respond, is so strong that it's a good approximation to assume it's 0.
Okay, thank you.
You're welcome. Any other questions? All right. So again, thank you so much, and I see you tomorrow, 9:15. Bye-bye.
See you. Thank you.